Welcome to Lesson 9 on Cauchy Riemann equations. If we break a function, a complex function, into its real and imaginary part, there's something called the Cauchy Riemann equations, these partial derivatives that I'm showing here. They give us a way to check whether the derivative exists without actually appealing to the definition of derivative directly using a limit. So this is a bit easier to use. And we'll get into the details of this. There's also a polar form. We'll talk about that also. Okay, as I noted, the Cauchy Riemann theorem gives us a way of verifying that a derivative exists. So we basically take a complex function and break it into its real and imaginary part. We've seen that already. The Cauchy Riemann equations, which are basically the heart of the theorem, need to hold true in order for this derivative to exist. So if you take the partial view with respect to x, that should equal the partial view with respect to y. And the partial view with respect to y needs to equal the negative of the partial view with respect to x. And of course, we evaluate these at a given point if we're interested in differentiation at, say, just one point. But normally, we'll do it for the entire domain of the function. So just as a refresher, the partial derivative is when you have a function like we have here, u of xy. If we take the partial with respect to x, we treat y as a constant, and then we just take the derivative of x. And similarly for these other three partial derivatives. Yeah, and then just one other point. There's another notation which I've shown here. U sub x is another notation for the partial view with respect to x, and you can have v sub y and u sub y and v sub x and so on. So you'll see both of these notations in the literature. The converse of the Cauchy Riemann theorem is also true. So if the partial derivatives of the real and imaginary parts of a complex function f of z exist, are continuous, and satisfy the Cauchy Riemann equations at a point z0 equals x0 plus iy0, then the derivative exists at the point z sub 0. And we also have this two alternate forms for the derivative. We can just plug in the partial derivatives here, either with respect to x in this first case here, or with respect to y in the latter case. So the proof of both the Cauchy Riemann theorem and its converse, you can have a look at Orloff's online book. It's part of the Libra text series, so it's free of charge, and that'll give you the proof. Just to give you a quick sketch, the way we get this is, if you recall from our earlier example in lesson 8, when we showed that the derivative of the conjugate of z did not exist, we took the derivative along the positive y-axis and the positive x-axis and showed they weren't the same. So if you do that in general for a function f of z, and you take the derivative along the x-axis and then the y-axis, and you compare the results, but you're going to get some general formats for each result, you're going to end up with these partial derivatives, and you're forced to conclude that u of x, u sub x, the partial of u with respect to x equals a partial of v with respect to y, and a partial of v with respect to x equals minus the partial of u with respect to y. So that's the sketch of the proof. It's kind of long, and I thought maybe it'd be better just to do an example and not spend too much time on the proof of that. And so we do have an example here. It's the same one we did before, but except it's much easier when we use the Cauchy Riemann equation. So we have our conjugate of z. We break that into the real and imaginary part. We take the partial with respect to x. We get 1. Partial with respect to y is minus 1. so they don't equal. We could stop here, but just for the completeness, when you take the partial with respect to y and of u and the partial with respect to x of v, you get 0 in each case. And so since this doesn't hold, we can conclude from the Cauchy Riemann theorem that f of z is nowhere differentiable. All right, we're going to try a little bit more complex example. In this page here, we have f of z equals e to the z. And we want to show that's differentiable. So we're going to use the converse of the Cauchy Riemann theorem. So the first step is we want to write e to the z in terms of its real and imaginary parts. So we write z as x plus iy. Then we break it into two parts here. And then we use the Euler formula on e to the iy. We multiply through by e to the x, and we get this is our real part and this is our imaginary part. So u of xy is e to the x cosine y, v of xy is e to the x sine y. Then we take the partial derivatives of u with respect to x. Remember, when you take the partial with respect to x, the y is basically treated as a constant. So you just get e to the x cosine y. Then you take the partial of v with respect to y. X is treated as a constant in that case. Derivative of sine y is cosine y. So you get equality here. That's good. We do the second of the two Cauchy Riemann equations. The partial of u with respect to y is e to the x is a constant now. Derivative of cosine y is minus sine y. So we get this. Then we go to take the negative of the partial of v with respect to x, and we get the same thing again. So the equations hold true. These are continuous functions. And not only that, we have the bonus that if we can plug in u of x, v of x into our formula here, and this is the derivative. I should have written here, this is derivative of f with respect to z. This is what I'm drawing out here. So you plug these in, you factor out an e to the x, you use Euler's formula in reverse, so to speak, get e to the x, e to the iy, e to the x plus iy, which is e to the z. And we kind of knew that, right? The derivative of e to the z is itself. And so we've shown that using the Cauchy Riemann theorem. There's also a polar form. And the way we do that for the Cauchy Riemann equations is we first write f of z in terms of the real and imaginary part, but the real part is written in polar form and the imaginary part is written in polar form. And the equations we get are these here. So the partial of v with respect to the argument theta equals r times the partial of u with respect to the r, which is the modulus of z. And then we get the second equation here. And once you do this, once you compute these partial derivatives in polar form, the derivative of the function is given by this formula here. And again, this holds in both forward direction, and the converse is also true. So if these two hold, then this is the derivative of the function. If these are false, either one of them are false, then the function does not have a derivative. On this slide, we'll use the polar form of the Cauchy Riemann equations to establish the derivative of 1 over z to the n. We first write 1 over z to the n in polar form. We substitute in r e to the I theta for z. We raise this to the power n, we get these two terms. And then we can bring e to the I n theta to the top, putting a minus sign here. And then this is using Euler's formula, cosine n theta minus I n theta. And remember, the cosine of a negative of an angle is just the cosine of the angle, but the sine of a negative of an angle is negative sine of that angle. That's why we have the minus sign here. So we get the multiplying through by 1 over r to the n, we get the u, the real part, and then the imaginary part. We take the partial derivatives. V with respect to theta is just n cosine n theta over r to the n, and we have the minus sign. Get that here. Then taking the derivative, partial derivative of u with respect to r, and then multiplying by r. It's what you have here. You have r times, and the derivative. Basically, when you're taking the partial with respect to r, you treat the theta as a constant, so that just comes out. Then you have the derivative of r to the minus n. This expression here. You bring r to the minus n minus 1 to the denominator. You have that. Then you cancel the r with the 1 here, and you get the same expression as we have here. Then you do the same for u with respect to theta. You get minus n sine of n theta over r to the n. And then you need to take minus r times the partial of v with respect to r. And it's similar to this computation. I won't do that again, but you can do that as an exercise if you like. So we're almost done. We need to plug in our formula into our formula for derivative here, which we had from the previous slide. So use partial of u with respect to r. You divide r into this, and you get this expression here. Partial of v with respect to r, again, you have to divide the minus r into this, and you get this here. You factor out the n, the r to the n, or 1 over r to the n plus 1. You can bring the e to the minus theta down into the denominator. Then this, what's left, is actually e to the minus n theta. That's from Euler's formula. E to the minus n theta you can bring into the denominator. So this becomes e to the I theta n times n plus 1. So both of these terms in the denominator are raised to the n plus 1 power. And then you can replug or resubstitute back z in for r e to the I theta, and you get minus n over z to the n plus 1. Okay, so quite a long story, but this would be still much easier than trying to do this via the limit formula for derivatives. So that's it for the Cauchy Riemann equations. They're quite useful, and we'll be seeing those more in some of the future lessons.